Good morning, everyone. With this short presentation, I would like to give an update on where we stand with predictions for laser verification systems using early data release 3 from Gaia, and basically what we have also done over the last few years to improve the sample of verification systems. And so let me start out with a first presentation of a survey, a dedicated survey to find these systems. So this survey has been executed with the Zwicky Transient Facility, which is a sky survey located at Mount Palomar in Southern California. And the idea is really to observe the sky repeatedly to search for changes in brightness on the sky. And so as part of the Zwicky Transient Facility, we actually developed a dedicated survey to find these verification systems. And so the idea behind the survey was that you select a field, a particular part on the sky, and you observe this part of the sky repeatedly, continuously, over an hour and a half to 3 hours. And so the idea is if something changes in brightness periodically over an hour and a half or 3 hours, you would expect that this is actually a very short period binary. And these brightness changes could come from eclipses, they could come from ellipsoidal deformation, and so on. So there are different things, and you would only expect these very tight verification systems to show up or show these brightness changes over the period of an hour and a half to 3 to 4 hours. So the way we did this survey was we actually looked for the highest stellar density. And so that's what you see in the upper panel here. You see this yellowish shaded region, and that's actually the galactic plane. That's where most of the stars are. And these orange and red boxes on top of that show the fields we selected to being observed. So each of these squares is actually an individual CTF field. So all of these fields were observed. And as you can see, only in 2018 and 2019, we already covered a substantial fraction of the galactic plane with this survey. And so we really covered a total, as part of this survey, a few 100 million individual stars, which makes it very challenging to find the verification systems, which are obviously very rare still. And so just to give you a bit of an idea of how to extract these variable sources, well, the first thing or the easiest thing what we did was, well, we took a field, a particular field, and I'm showing you one example, which has a median density. So this particular field in CTF has just 5 million individual sources. And that's the plot I'm showing here with the 16 individual small squares. And these are actually individual CCDs of the camera. And we extracted these 5 million individual sources. We calculated different light curve statistics because variable sources will have a different statistic than a constant source. And then we basically look for variability. And so we find that about 1% of all the sources in the survey are physically variable over a time frame of hours. And so that's still, that means, well, that's now a low number. Well, if you had started with 200 million sources, that's still a few million sources to look at. And most of these sources are not verification systems, obviously. Most of these sources are pulsating stars, flaring stars, and so on. So these are really the significance. So now it's really to the point where you have to find these verification systems out of this whole bunch of other variable sources. And I'm showing here one example where we actually, this is a verification system, a new one, which really stands out with a high statistical variability and was found to be a verification system. And just to give you a bit of an example, a few examples of what we have found in this survey. And so the upper two examples are actually what we think are new verification systems. The upper left is actually a new, or the first example of a helium star transferring material to a white dwarf with a very tight system. And then the upper right is a double white dwarf system, which is eclipsing. And you see these few data points which are below the continuum level. These are actually in eclipse point. And I think this really shows how difficult this search is, because you really have to find these very short duration eclipses, which for a 24-minute system, that's only a minute or two. It's really, really rapid eclipses. And so these few in eclipse pointers mark that. And so I really encourage you to look up these papers by Kevin Birch from last year, where he presents a good sample of new verification systems, and then also the example of where we found a helium star, accreting helium star into a white dwarf. If you also care about other things, then this is really a treasure box too. So for example, we discovered a new class of pulsating star, helium star pulsating stars with pulsation periods of 3 to 8 minutes. We have a sample of a few thousand flaring stars in this, which flare durations of an hour. So these are really, really short flares, which if you only observe once a night, you would not catch at all. And so we have now this beautiful sample of this well-sampled light curves of flaring stars. But now back, and let me take a step forward and now see what actually has changed from our last presentation and like with Gaia DR2, now going to early data release 3. Well, the first thing I want to say before I talk about the sources is if you compare the precision of parallax compared to DR2, we actually find that on average, roughly, the precision is about 30% better to DR2, which is great. Because if you have this higher precision in parallaxes for DR3, you get a higher precision on the actual distance. And you actually eventually, when LISA produces data, you get a higher precision on the trip mass, right? If you know the distance, you can actually estimate the trip mass. And so you get a higher precision on that. Because the point really is Gaia doesn't really measure parallaxes, distances, but parallaxes. And so the way you have to convert these historically, going from a parallax to a distance, is just by 1 over the parallax. That works only well for if you have a very high precision on the parallax. If the precision is relatively low, if you have high error bars, then you can actually do a better job by applying, including prior knowledge of the distribution of sources you're looking at. And so that's what we have actually done. So what we did to estimate the distance was we used Bayes' theorem. And what we did as a prior, we adopted an exponentially decreasing volume density prior with a given scale length. And so the scale length depends on what population the source has. Could be a thin disk, could be a thick disk, could be a halo. Each of those have different scale lengths. However, I want to make the point, if this parallax uncertainty is less than 10 to 20%, and many verification sources that have a very precise parallax, the distance is actually independent on the prior. So no matter what prior we're using, the distance comes purely from the parallax measurements. And so what we did, we calculated the galactic motion of each candidate source. And I'm showing you here in this plot about 50 candidate sources, show the motion in the galaxy of these sources. And then we basically estimate what's the population. And so here is an example where we show the eccentricity over the angular momentum vector in c direction of the galaxy. So that's really the elliptic, how elliptic these orbits are in the galaxy versus the angular momentum vector in c direction. And so you see most of the sources actually fall nicely where we would expect thin disk objects. So that actually shows that actually most of the sources we are seeing in the population are thin disk. And so we apply the appropriate scale lengths then for this particular source, use this to calculate the distance, and then basically go from there and use this distance to estimate the LISA strain and so on. Right? So this is how we did it. So the point is most sources are actually thin disk objects, and many sources have a parallax uncertainty low enough that the prior doesn't matter too much. So before I show you the new results, let me actually take a step back and show you what we had in 2018. In 2018, we had the sample which had a large overrepresentation of accreting white dwarf AMCVNs. And because at this point, they were easier to find, all of these sources were most of these sources were serendipitous discoveries, where there was a blue source, somebody took a spectrum, oh, that's an AMCVN, oh, this has a very short period. It could be a verification source. And that really shows this overrepresentation of AMCVNs about 2 or 3 years ago. And you also see the filled symbols represent eclipsing sources. And at this point, we had a few eclipsing sources. So now with these new surveys, and particularly with the CTF survey to search for these systems, this picture has changed quite a bit. So now we are talking about many more double white dwarfs. I think we are now close to equal number of double white dwarfs as verification systems. And because the discovery method was all typically for the matrix, a lot of these NOR sources are actually eclipsing. So that's why we have now this much larger number of eclipsing sources compared to what we had before. And so the number now increased quite a bit. And you see these starting to do these systematic searches, you get the better estimate. However, although this Galactic Plane survey was sort of and the CTF survey by itself was kind of a systematic survey already, it only covered the northern hemisphere, and it's only sensitive to eclipsing sources and sources which change their brightness in photometry. Sources which don't, we would not expect to see. And so AMCVNs, as an example, do not really change their brightness a lot over when you observe them. And that's why we haven't really seen a lot of new AMCVN systems in these surveys. And because of the discovery method or the location, most of the sources we know of today are actually in the northern hemisphere. And that's what I'm showing here is the sky distribution of the known sample of verification systems. And you see they're very heavily skewed towards the northern hemisphere. In fact, in the southern hemisphere, there's not really a single double white dwarf known yet so far. And so this hopefully will change in the near future when things like BlackGEM come online, and then in a few years, the Very Rubin Observatory, which will, for the Very Rubin Observatory, because of the slow cadence, it will take a few years until you can effectively search for these systems, but these things will change over time. And so as more surveys come online, we should also find in the southern hemisphere more surveys. So although I really think over the last few years, this more systematic approach really shows its first fruits, we're still only scratching the surface. And that's really the final point I want to make here. Although we have made this progress, we're only scratching the surface. And what I'm showing here is actually a Hertzsprung-Russell diagram of these of all the sources now, which we would call verification systems. And you see that even the double white dwarfs lie above the white dwarf track. So the white dwarf track is this light grayish area in the lower left. And you see all of them are just still brighter than where most white dwarfs actually are. And the reason is, again, purely easier to detect. Systems are brighter, they're brighter in the sky. So that means you can find them easier. Typically, white dwarfs on the cooling track are much fainter. So that means they are also fainter on the sky. You can only look at a smaller volume. It makes them much harder to find. And so that's really the reason why at the moment we still are biased towards these more luminous sources because they're just easier to find. Nonetheless, I think the numbers have increased quite a bit over the last years. We are now roughly at about 24 systems, which we would give find an SNR of larger than 5 in LISA after 10 years of observing with LISA. And so showing that I think we have made good progress, but there's still a lot of space for even more improvement. And I hope we'll do this over the next years. And with that, thank you very much. And I'm looking forward to discuss these things at the meeting with you.